So Archimedes is going to take these exact numbers and impose them on this triangle. So Archimedes is going to say that this length from the center of the circle out here to the perpendicular is going to be the square root of 3. Then he says, all right, so the riser must be 1, and the length from the center here out to this perpendicular is going to need to be 2. Now, because of this, he's going to be able to start working on this problem. Now, the first thing we know is this. If half of one of the sides of my hexagon is 1, a side of my hexagon is 2. 2 times 6 is 12. All right, so the perimeter of this sixagon is 12. What would be the circumference of this circle? Well, this circle we know has a radius of the square root of 3, so it would be, the diameter would be 2 times the square root of 3 times the number today that we know as pi. I'm going to estimate this at around 3. So 3 times 2 is 6, and the square root of 3 is about 1.7 if I remember correctly. So we do have a number that 6 times almost 2 is almost 12. So we see that the circumference and the perimeter are not that far apart. Now, we have the first step of the problem. Now, let us see about working the second step in this problem, which is when Archimedes said, I can do better than this. So let's watch. And we come back and we now have a dodecagon. 12-sided. Now, because this is a 12-sided figure and it's hard to see, let me do something to help us for a moment. I'm going to hide the hexagon, and I'm also going to spread this circle out. But I think we can agree pretty quickly that a dodecagon is a pretty doggone good estimate for a circle if when you look at these sides, they're not really getting that far off the circle. Now, the question is that we must answer is how in the world do we come up with this little distance right there? If I can determine that distance, I can then calculate the perimeter of the 12gon and continue this idea of squeezing down on what is pi from above. So in order to do that, let's think about what we need to know. Well, we know the length of this triangle's leg right here from the hexagon. We know the height total. We know the distance over. What we need to know about is this little triangle right here. Well, we know parts of it. We do know that this radius has not changed. It's still square root of 3. We still know that this distance up here is going to be 2, and I know this total length here is still 1. But how does that help me find this smaller triangle? Well, let's keep something in mind. I have some ideas about how certain triangles work, and one of them is, if we go back and look at this, it shouldn't be hard for you to prove, and we're going to do it right now, if I have a 12-sided figure that's regular around a circle, that means that the central angle is 360 degrees divided by 12 marks off any one of these dodecagon sides. So 360 degrees divided by 12 is 30 degrees, which means that this little angle right here is 15 degrees, exactly half of the original 30 degrees. From the previous video that you've watched, you now know something. Let's label some of these sides. And I'm going to label this as A. The center of my circle I'm going to label as O. We're going to label this point up here on the hexagon as B, and this on the dodecagon as C. And we know because we're taking a triangle and we're splitting one of the angles equally, there's some ratios here that we can talk about. And basically what we know is from O to B, is to B to C just as O to A is to A to C. We know that ratio must work. Now let's think about the bits and pieces we know in the way of numbers. We know O to B. So I'm going to circle that. That's a known value. B to C is unknown. O to A, known, not a problem. A to C, unknown. Doggone. I need one more piece. But aha, we're in good shape. Let's watch what I can do. So we know that these two pieces that we have, I want to put them together. So what I'm going to do is I'm going to have AO, just flipping the order around. I'm going to move BO underneath that, and I'm going to move the AC up here over the BC. So this ratio must also work. No problem whatsoever. Now, what we're going to do now is we're going to use one of the rules that we get from ratios, which is you can add 1 to a ratio and it really doesn't mess things up. Let's watch. So, let's add the denominator to the numerator of each of these. And I'm now going to get AC plus BC over BC. I added 1. Must be the same as AO plus BO over BO. Now, remember, all of this is known to us. No problem whatsoever. BC, we don't know. But now I have AC plus B to C. Well, notice A to C plus B to C, I can replace this piece with known information, which is A to B. So this is the same as saying A to B over BC, and AB is a known value. So what's that going to allow me to do? The only unknown is now what? B to C. So what I'm going to do is I'm now going to mark this piece right here as known. Now why is that impressive? If I know this piece, and I know A to B, it means I can do some subtraction and I can now find this piece. Now think about it, we have a right triangle here. I now know the horizontal bit, I now know the up and down, which lets me find the hypotenuse. I can solve for this entire triangle right here. Now why is that impressive? Well, what am I going to do next if I'm Archimedes? I'm going to take this known triangle, I'm going to split this angle here in half, and I'm going to do the same thing again. And this is going to let me then take known answers from my 6-sided hexagon, gives me my 12-sided, my 12 will give me my 24, my 24 gives me my 48, which gets me to 96. And if you think a 12-gon is close to a circle, a 96-gon is going to be real close to a circle. And we're going to figure out how close. So let's move on to that part of the video.